There we are. Now we're on. Yeah, so it's great to be here. It's great to walk outside without having to put an overcoat on. It's a beautiful campus, so thank you for inviting me. And I've really enjoyed myself today discussing physics with your various colleagues, and going to be here tomorrow too. So that's a lot of fun for me. So I think this needs to go a little bit lower down. How about that? Yes. This year, 2025, is actually the 100th anniversary of quantum mechanics. And so I'm going to tell you today a little bit about the history of quantum mechanics and give you my perspective on what was happening 100 years ago as a lowly solid state physics. Of course, solid state physics didn't even exist 100 years ago. Itself is a consequence of quantum mechanics. So my talk is entitled A Solid State Physicist Reports from the Halftime Show. And you might be saying, halftime show? It happened 100 years ago. What do you mean? Well, that's part of the theme of today's talk. I really do believe we're at the halftime show of quantum mechanics, and I'll try to explain to you why that's the case and why this is a really exciting time to be involved in quantum theory and its various activities. Okay, so let's see if this works. Good. And so the work, the talk I'm going to give today is in part due to many, many discussions I've had with my partner, wife, Premi, who is also a physicist. And so I'm thanking her. We love to talk about physics and what was going on, what people actually thought. When she was a little girl, she was given a blue dog by a gentleman who asked her, do you think there can be blue dogs? And that gentleman was Paul Dirac. So we feel that we have a little connection with the past, okay? So UNESCO has made this the International Year of Quantum Science and Technology. And it's really an opportunity to share the excitement and tremendous achievements of our field. Quantum mechanics didn't occur in 1 year. And so this is a celebration that will really be part of this decade. For many of us, quantum mechanics is truly personal. It's something we use on a regular basis. It's probably the thing that drew us into physics in the first place. And so this is quite an opportunity for all of us. Okay? And it's a chance to reflect on what is, I believe, a continuing revolution and its potential for new discovery and technology. And I hope when you go away from my talk today, that you will share with me the viewpoint that we're at a really exciting point of discovery. We are not just 100 years after all the interesting stuff took place, but we are right slap bang in the middle of an amazing time. Okay. So this is my outline. I'm going to tell you about the history. And then I'm going to switch to talk about why I think we're only halfway through. And we're going to take our cue from looking at the Newtonian revolution. And then I'll tell you a bit about some of the challenges that are there, the dark matter challenges, not only the cosmological challenges, but also the dark matter challenges right under our nose in the laboratory. And then we'll end talking a bit about some of the deep challenges of quantum mechanics, the nature of information, and beyond Copenhagen, okay? And please interrupt me, okay? So 100 years ago, a remarkable sequence of discoveries took place that led to the birth of modern quantum mechanics, and it involved a tremendous cast of characters from Planck to Oppenheimer. This is an incomplete list, but I'll tell you a little bit about the contributions of these various gentlemen over the course of this early heroic period. Okay, and so if you want to read more, let me encourage you to look at this marvelous book, Sources of Quantum Mechanics, which was originally compiled by Max Born and put together by Van der Waarden. And one of the conclusions of this book, and many of those who were involved in the early quantum days, is that the research and the transition from classical mechanics to quantum mechanics was really a process of systematic guessing, guided by the notion that in the limit of macroscopic physics, quantum mechanics has to come back to classical mechanics, the so-called principle of correspondence. You may also like to read this article by Christian Camilleri in Nature on the 8th of January, how quantum mechanics emerged in a few revolutionary months 100 years ago. Okay, and it really is 100 years ago from now when it was all happening. Okay, let's look back a little bit and remind ourselves of the early signs that were there before the quantum revolution took place. And of course, this was the era of Planck, Einstein, and Bohr. What did they do? Well, let's first think about that, okay? So based on Planck's work, Einstein argued that light is composed of particles. We call them photons today, okay? And we ascribe to them this marvelous relationship between frequency and energy. We think of them as little packets of energy, okay? And this answered why hot things change color, something that couldn't be understood classically. But it also opened a Pandora's box of questions, which continues to this day, and which is the epitome of it is the question of how can electromagnetism be both wave and particle-like? And the way we deal with this paradox today is we just call it a duality. We call it wave-particle duality, but anyone who's spent years studying this still finds it paradoxical. And it is part of the core of quantum mechanics. This is the other gentleman that we're going to talk about. This is Niels Bohr. Niels Bohr was a student, an assistant with Rutherford. And whilst he was working with Rutherford, he came up with this marvelous picture of atomic structure. This is Werner Heisenberg, who we're going to come back to shortly. And the reason I'm putting his picture up there, even though before the Second World War he was just a lad, is that he has a nice recollection of his first feeling meeting Niels Bohr. Okay? And he describes how he met him for the first time in 1922. He would have been someone who had just finished his PhD work in 1922. And he met Niels Bohr in Göttingen, and they called it the Bohr Fest, which they used to hold at Göttingen. And he describes Bohr as being full of youthful excitement, but a little self-conscious and shy. He dipped his head to one side and he stood on the platform of the auditorium with the Göttingen summer light streaming in through the windows. And one of the things he loved to do was to philosophize. And he spoke softly with some hesitation, but behind every carefully chosen word, one could discern a chain of thought which eventually faded somewhere in the background into a philosophical viewpoint which fascinated me. And there was a lot of philosophical discussion in early quantum mechanics, a lot of questioning about what it meant, what observation meant, what we could truly actually observe. So what was it that Bohr had done? He was fascinated and driven by the sharp emission lines of atoms. We all know that when you look at the emission lines of an atom, they're discrete, and Bohr pondered over this and reasoned that if photons come out with discrete frequencies, then the atoms must exist in states of discrete energy. Okay? And these are the famous stationary states. And these stationary states, of course, play a central role in our understanding of quantum mechanics. Anytime we have any doubt about whether stationary states exist, we only need to think back at the emission lines of atoms. Okay? And so the theory of Planck and Einstein and Bohr established many of the key concepts of quantum physics, the photons, the idea of stationary states, quantum numbers, and this peculiar concept of wave-particle duality. And these would all feature in the new quantum mechanics. Of course, in the meantime, there was a terrible world war which eviscerated a large part of the male population. And so the physicists to emerge on the other side of the war were either those who were too old to serve or those who were too young to have served. Okay? So let's look at the birth of the electron wave. And this took place after the First World War. And it was a time of disruptive change in science, in economics, art, and politics. This is a theoretical paper taken from 1922 in which the German physicist Ladenburg analyzed in great detail the spectrum of hydrogen. And they knew a lot about the spectrum of hydrogen and the energy levels. They could label them with quantum numbers, but they didn't understand the principle that lay behind the stationary states. This is a picture from Picasso in 1924, Guggenheim. Picasso was an absolutely brilliant technical artist. And he used that technical artistry to push ahead in the avant-garde. And this is also true of our early quantum physicists. They were all masters of classical mechanics, masters of electromagnetism, and they used their artistry to push the ideas forward in a very avant-garde direction. And last but not least, here is a picture of a real note from 1922, I believe. This is the 10 to the 12 mark from the Weimar Republic. Billion in those days meant 10 to the 12. And hyperinflation was so huge in those days that they were forced to print marks of such large and vast value. Okay, this was a time of great disruption. Things were not going so well in Germany. There were many political assassinations. This is young Louis de Broglie, age 27, one of the few quantum mechanicists who was actually born in the 19th century. And he thought about the wave-particle duality and wondered whether it might work in reverse, that particles might be waves. And in his thesis proposed that electrons are waves. And with this idea, he was able to account for Bohr's quantization condition. And he was able to generalize the idea taken from photons that there's a relationship between the momentum and the wavelength. So this is his celebrated equation, lambda equals h over mv. I don't know what's going to happen next. And his idea allowed the structure of the atom to be understood in terms of standing waves. Right? Now, this idea seems very commonplace to us today, and we wonder why it might not have been figured out earlier. Why didn't Bohr come to the conclusion that electrons were waves? Well, in fact, it may seem normal to us today, but at the time, it was rather radical. And there were great mathematicians and physicists on Louis de Broglie's thesis committee, but they felt that they weren't able to evaluate his work. There was Cartan was on his thesis committee. And so they sent it off to Einstein, and Einstein thought it was amazing. He said he's lifted a corner of the great veil. Can you imagine if you had such a commentary from the great man on your thesis? But it raised lots of questions. And peculiarly, the question was there experimental evidence for it? And the evidence for this took place on this side of the Atlantic in New York City. This is Davison and Germer, who were working at Bell Labs in 1924 when their vacuum chamber broke. They had to re-anneal the metallic surface they were sending electrons into, and somehow this improved the quality of the crystals. And when they sent electrons through the crystals, they saw they diffracted. And moreover, the angles of diffraction were completely consistent with the wavelength predicted by de Broglie's equation. So this was the situation in 1924. By the way, if you come over to New York City and you take a walk on the High Line, you can actually see a plaque halfway down, which is at the location of the old Bell Labs, which is where this measurement actually took place. Rather remarkable to think that one of the major discoveries of quantum mechanics took place in the heart of New York City. But what were the waves? Did they pilot the electrons as de Broglie thought? De Broglie was an accomplished mathematician, And it's rather surprising that he didn't try to write down the wave equation that went with this. We don't know why he didn't do that. Okay, and what new kinds of mechanics was needed. So over the next few years, Heisenberg, Born, Pascual Jordan, Paul Dirac, Pauli, Schrödinger, with several others, went on to formulate what became the mathematical framework of quantum mechanics. Let's look at this. Let's take a dive into this transformation that took place in the next few years. And before we do that, lest you think this was entirely a European story, I wanted to mention that in addition to this seminal measurement in New York City, there were two young Americans who had major early impact and actually influenced the work by Heisenberg. And strangely enough, almost nobody knows the names of these two young Americans. Anyone know who they were? What is it? No, he was not one of them. He's on my list up there, but he wasn't one of them. In fact, I haven't put them up here, so you can't tell from that. Who were they? Anyone know? Okay, well, let's look at them. Okay. John Slater, age 24. He wrote a letter to Nature in 1924, which got him invited to work with Kramers and Niels Bohr in Copenhagen. And this is what he wrote. He wrote that any atom may, in fact, be supposed to communicate with other atoms all the time it's in a stationary state by means of a virtual field of radiation originating from oscillators having the frequencies of possible quantum transitions. I think that's a really amazing statement. It's the germs of the idea of virtual transitions. Okay? And he went on to write a famous paper with Kramers and Bohr, which he later regretted writing because it gave up on energy conservation, and he wasn't at all happy with that. And as we know, you don't have to give up on energy conservation in quantum mechanics. Okay, this is John van Vleck, and he also came from Harvard and went across to Europe, and he studied the Bohr orbits or the semi-classical orbits and came to the conclusion that was growing at the time that the frequencies of the oscillators are the spectroscopic ones rather than the frequencies of the orbits. Classically, you would imagine that the frequency of the radiation coming off would be the frequency of oscillation of the electrons in the orbits. But at this time, they began to realize that you had to transform into a new picture in which those frequencies are determined by the Bohr condition. Okay. So let's look at the leap. 1925, 1926, 100 years ago, an amazing transformation took place. And this is the guy who precipitated the transformation, Werner Heisenberg. And he had been a postdoc with Max Born. He was 23 years old. And he'd been thinking about a way to completely transform quantum mechanics into a new structure. And at the time of June 1925, he escaped to Helgoland because he had intense hay fever and there were no flowers on Helgoland. And when he returned to Göttingen 10 days later, his insights had crystallized into the basis of modern quantum physics. Here is Helgoland. And if you were lucky enough to be out there in June, there was a nerds party to celebrate the discovery of quantum mechanics. I suspect there was a lot of merriment. So this is what he wrote when he came back. He said, all my wretched efforts are devoted to killing the concept of orbits completely, which cannot be observed anyway. He, in fact, sent a copy, his only copy of his manuscript to Pauli and asked him to send it back to him when he'd finished reading it. In fact, the next part of this letter was he wasn't sure whether he might just burn it when it got back, because he was really uncertain about it. Okay. Let's take a deep dive into what he actually did in this paper that he was persuaded by Born to submit to Zeitschrift für Physik on the 29th of July. In fact, Born sent it off for him. So here are the key elements of this paper. First of all, he takes this idea that we heard from Van Vleck, that the frequency is determined by the Bohr condition, an oscillator with a frequency determined by the Bohr condition. Okay. And the second point he realized was that the amplitude of displacement of this oscillator has to depend on the initial and final state. In other words, it's an array of numbers which depend on the initial state, n, and the final state, n minus alpha. And so this is the way he wrote the displacement, okay? And he realized that he had to have a rule for combining, for squaring and combining x with y. And in fact, he didn't know, but what he had discovered inadvertently was the matrix. Born told him later that this is a matrix, and this is then the origin of matrix mechanics. But Heisenberg didn't know about matrices. In fact, most physicists didn't know about matrices at the time. It was a completely new concept, okay? So this is what this is an equation from his paper showing how you multiply two of these amplitudes together. If you have two transitions, you have to multiply the amplitudes like this, Heisenberg speculated. Now, what model should he use for his oscillator? An atom much too complicated. So what he looked at was the harmonic oscillator, but the anharmonic oscillator. And he reasoned that because of the correspondence principle, that these x's would have to follow the same equation of motion as in the anharmonic oscillator. This is his basic assumption. And then he needed to add in quantum mechanics. And so here he took the old quantum mechanics, and the old quantum mechanics had this condition that the action associated with the closed orbit, PdQ, was equal to a multiple of Planck's constant. Okay, so he took that and he wrote it as a differential equation. And so H is then the derivative of I with respect to n in the large n limit, in the correspondence limit. And then he plugged in this formula for x that he'd written already and got this continuum equation, and then thought, well, that's okay when n is very, very large, but what about when n is small? What should I do? And he then discretized this equation, and this is the discrete version that he speculated on. Now, where did he get this equation from? Well, it was guessing, but in fact, a very similar equation had actually been proposed by Kramers earlier in his study of absorption and emission lines. And so he could see the relationship between Kramers' expression and his quantization condition, and he speculated that this should then be the quantization condition. And if you actually look at that with a modern eye, this is in fact the expectation value of the commutator being equal to Planck's constant. Yeah? So this was the key thing, and from this, he was able to go back and look at the equations of motion and adjust things in such a way that he get a kind of diagonal equation. All the coefficients worked out. He was basically solving this matrix equation, and he was able to work out the quantized energies which contain this nonlinear term here. And it's interesting to go back and actually try to reproduce this with modern technology. And with a bit of effort, maybe a mathematical code or two, you can get the numbers out, and maybe you make a mistake or two. But when you finally come down to it, you discover that Heisenberg was absolutely dead on. There's no factor of 2 error in his result here. This is absolutely the modern value for the anharmonic oscillator. Okay? This was not a fellow who was approximate. He was a very precise physicist. Okay? He'd done this, but he wasn't at all sure that he'd got it right. And the final paragraph of this paper, in its English translation, he writes, whether a method for the determination of quantum theoretical data from relations between observable quantities, like the one that was proposed here, can already be regarded as satisfactory in principle, or whether it represents only one more much too bold attack on the problem of formulating a quantum theoretical mechanics, will be clarified by deeper mathematical examination of the method that was employed very superficially here. And in fact, as I mentioned, he was of 2 minds as to whether he should not submit it, just burn the thing down. Okay, it's interesting to speculate what might have happened had he burnt it, and we'll see that in a minute. Okay, because we know the answer to that, I think. Okay, so this led to an earthquake of activity, and there were enough clues in his initial formulation of matrix mechanics to try to put together the full formalism. And we know this because 2 different groups came up with the precise formulation completely independently. Okay, so First and foremost, the first guys to get involved were Pascual Jordan and Max Born. They were masterful mathematicians, and so they wrote a paper on quantum mechanics. And a key part of this paper, the introduction, was the introduction to matrices for physicists. And you could read this paper today, and you can see what is a perfectly nice description of how to manipulate matrices, how to calculate their products, how to calculate functions of matrices. And here is one of the equations from their paper. Okay, but they also realized that Heisenberg's quantization condition could be formulated in terms of the non-commutivity of matrices, and they were able to pull out of it this famous commutation relation between P and Q, okay, and the equations of motion. These are all in this 27th of September paper. Look at that, just 2 months after Heisenberg submitted his paper. They spent the whole summer working on this. In the meantime, in fact, Heisenberg had visited England, and he hadn't actually spoken of his quantum mechanics there, but he left one copy of his paper for the British to look at. And Fowler, who was a theoretical physicist at Cambridge, didn't understand it, but gave it to his student Dirac to take a look at. And Dirac, this young gentleman here, just 24 years old at the time, spent the summer studying it and came up with exactly the same conclusions as Pascual Jordan and Max Born. But from a different point of view, he recognized the relationship between the commutator, what we call the commutator today, and the Poisson bracket. And so he wrote the equations of motion in the classical form. This is x dot equals x with h is the classical equation of motion for in terms of a Poisson bracket, but he related x, the commutator of x with h in this way. This xy with minus yx is then the Poisson bracket times h over 2 pi, okay? And so he also identified matrices as canonical transformations, okay? It must have been very frustrating for him because probably shortly before he submitted his paper for publication, he probably received the paper from Born and Jordan. Must have been very frustrating to realize you worked all of this stuff out. You thought you were the very first, and then to discover these two Germans describing everything, and they just pipped you to the post. Nevertheless, he kept working on it. And 1 week after he submitted his paper to the Royal Society, a second paper appeared. This was on quantum mechanics too, by Born and Heisenberg. And in this paper, there's the first hint of the notion of states, quantum states. By the 17th of January, Wolfgang Pauli had taken this phenomenon, this formalism, and used it to solve the hydrogen atom, and it worked out all the states of the hydrogen atom, the quantization of orbital angular momentum. And this was the state of affairs in early January. In fact, Dirac did a similar thing. He carried out a preliminary investigation of the hydrogen atom. In fact, it's rather entertaining to go and look at Dirac's paper without blinking an eye. He actually solves a 2D version of the hydrogen model, hydrogen atom, not a 3D version. And there's no explanation whatsoever why he chose 2 rather than 3 dimensions. It was perhaps because it was an easier calculation to do at this early stage. So this was the scene at the end of January 1926. Okay. The operator framework of quantum mechanics was established, but wave mechanics had yet to begin. And so this brings us to the second part of our story, this gentleman, Erwin Schrödinger. And he had read a little bit of the Göttingen work, and you can't see it there, but it says, repelled by the Göttingen approach to quantum mechanics. There's a quote he made to one of his friends in a letter. He just didn't like this way of doing things. He was 39 years old in 1925, and so here's the backstory to what he did. Schrödinger gives in Zurich a colloquium on de Broglie waves in December 1925. And physicists have always been a little bit cruel to one another, and this was no exception. Peter Debye to Schrödinger said, well, Schrödinger, you're not doing anything important these days. Why don't you see if there's a wave equation? Rather remarkable remark, because it's a kind of throwaway remark, you know, it's a small thing you might look at, okay? And Schrödinger took him very seriously. He spent his Christmas and New Year in a sanatorium, a vacation spot in Arosa. He was a ladies' man, and he went off with his mistress, his girlfriend at the time, not his wife, and worked away for 2 weeks on what became the Schrödinger equation. And this is a page from his notebook. We know of his calculations, but we don't know who his mistress was. His wife burnt that part of his agenda book. Anyway, so this is the Schrödinger equation of the time. And on the 27th of January, he sent off his paper, Quantization as an Eigenvalue Problem, with his solution to the hydrogen atom. So his was not the first solution to the hydrogen atom using quantum mechanics. That was, pardon?
Still upside down.
Yeah, that's the notation he used at the time.
That means del squared.
That means del squared, yes, yeah, that's right, yes. So, in fact, in 1926, Schrödinger had an explosion of activity, and the first paper in January, the second in February, the third in May. In the third paper in May, he had a discussion of wave packets. This is a picture from his paper in May, in which there's also a solution using Schrödinger's equation of the harmonic oscillator. Going on, there is the time-dependent Schrödinger equation appearing in June of that year. And in March of that year, he also proves the equivalence of matrix mechanics and wave mechanics. It's true that this was an early proof of the equivalence, and a final proof of this equivalence had to wait till von Neumann's work in the 1930s. But amazing that just 2 months after his Schrödinger equation, he had basically shown the equivalence of the two methods. And this is a matrix element in the language of, this is showing how to calculate one of Heisenberg's matrix elements from the Schrödinger equation. He also derived the many-body Schrödinger equation, the two-body Schrödinger equation in June, and also an early version of the density matrix. Okay, all of this in 1 year. And then finally, at the end of the year, he submitted the first English paper on quantum mechanics. He submitted what we would regard as a Rev Mod Phys to the Physical Review, an undulatory theory of the mechanics of atoms and molecules. This is a beautiful review of wave mechanics. Quite a year of activity for 1 year. In fact, this was his peak year of activity. This was his wonderful year. He went on to do many amazing things, in particular to pioneer the idea of entanglement in his discussion with Einstein, and biological physics. He encouraged many physicists, such as Watson and Crick, to switch to biology. They were inspired by a book entitled What is Life? But this was his peak year. And it's rather interesting to speculate that had Heisenberg burnt his paper in 1925 and not published it, he might still have gone on to do this remarkable stuff. Although we don't know, because we don't know whether the work by the Göttingen group stimulated him, even though he didn't like it. Okay. So this left open the major question of what is psi. And he thought it was an electron wave, that psi squared was the density of electron charge. And of course, it is. But we now know there's a probabilistic aspect to this. And this is Max Born, his advisor, who worked this out. Max Born, of course, realized that when you do scattering, a particle appears in the Geiger counter with a discrete arrival, a click, click, click. And that, in fact, to interpret Schrödinger's equation required a probabilistic interpretation of rho of x as being the probability of finding the particle, and the probability current as being the current of these waves. Okay. So by the end of 1927, Heisenberg had transitioned this into his modern uncertainty principle. And so by the end of 1927, a large part of the construct of modern quantum mechanics had been put together. Okay. This is a picture of the Solvay conference in 1927. It was a black and white picture. It's been colored artificially. And let me introduce you to some of the characters in this picture. Here is Planck, Einstein, Lorentz, and Marie Curie, the pioneers of the transition from 19th to 20th century physics. Marie Curie, pioneer of radioactivity, the only woman in the lineup here. Lorentz, a classical physicist par excellence, and Niels Bohr. These are the older generation, and the younger generation, de Broglie, Born, Heisenberg, Dirac. And so, sorry, I went too fast on all of that. Okay. And so by the time this picture was taken, the mathematical foundation of quantum mechanics was largely complete. Okay. But there was an important postscript that we have to talk about. And this postscript is very important for our modern understanding, and it links antimatter and LEDs together. It is the story about how this young British guy finally played catch up in writing down another wave equation. So Einstein had established the laws of relativity, but Schrödinger's equation only worked for non-relativistic electrons. What about relativistic electrons? There was a big push to solve this problem. And of course, Einstein's relativity results in this marvelous Pythagorean energy relationship between momentum and mass. M squared plus P squared equals E squared. Okay. And to get E, you have to take the square root of P squared plus M squared. And so one of the questions that then arose was, well, how do you take the square root of a wave equation? And around this time, someone went up to Dirac and asked him, what are you trying to do these days? And he said, I'm actually trying to take the square root of a matrix. And they were very puzzled, but it became clear sometime later what he was trying to do. And he succeeded. And this led to his relativistic wave equation. This is the wave equation. It's eminently simple. In fact, it's rather interesting that relativistically, quantum mechanics becomes a first-order differential equation. And this is the equation. It's one of the few equations that's actually inscribed inside a cathedral. Dirac's equation is inside Westminster Abbey in London. He was actually offered a knighthood by Queen Elizabeth, and he turned it down. They also offered to bury him in London, and this also was turned down. He is buried in Tallahassee, Florida. So how do you take the square root of the wave equation? That was the thing he came up with. And in fact, what it led to was this marvelous spectrum, Einstein spectrum, with the lowest energy being E equals mc squared, and it predicted spin. But it also predicted negative energy solutions. Not surprisingly, if E squared equals m squared plus p squared, you have negative energy solutions. And most physicists thought this spelt the end of Paul Dirac's ingenious equation. The general mood at the time for the next few years was that this was a very nice piece of mathematics, but it probably had nothing to do with reality. Okay? And of course, we now know that nothing is further from the truth. In fact, this wave equation is also the equation of motion of the field of the electron in the vacuum. Okay? And so Dirac came up with a beautiful explanation. It's rather interesting to note that he took rather a long time to do this, because initially he thought, okay, we have a filled sea of filled particles, and then if we take one out, we'll get a positively charged hole. And so far, so good. This explained what to do with the negative energy electrons. This then meant that the positively charged hole had a positive energy also. And so this was the whole theory of the vacuum, which we still use today. But Dirac thought that this positively charged hole was a proton. And he wrote this in his paper in 1928, one of his papers in 1928. And this is what he thought until 1932, interestingly enough. And two people played a major role in changing his mind. Okay, and here they are, Hermann Weyl and Oppenheimer. Okay, rather interesting that one was a great mathematician and the other went on to become the director of the Manhattan Project. Weyl and Oppenheimer played a key role in persuading Dirac that the hole was not a proton and must be the electron antiparticle. How did they do that? Well, Weyl did it purely on the basis of symmetry. He analyzed the group theory of the Dirac equation and said it can only be that if you had relativistic invariance, that the mass has to be equal to that of an electron. Oppenheimer did another thing. He said, okay, well, I'm happy to believe Dirac in the idea that the proton is the antiparticle of the electron. Let's calculate how long a proton would live in the center of an atom, of a hydrogen atom. What would be the lifetime of a hydrogen atom? And he came up with the result 10 to the minus 15 seconds. Okay, so that was the end of that idea. And these two things together led to Dirac publishing his change of heart in 1931. I said 32, but I should have said 31, 6 months before the observation of the positron. Okay, I'm missing a quote that he gave at that time. In fact, the paper he wrote at that time also includes the prediction of the existence of the monopole. And it also includes a rather long statement about how it's really important to follow the mathematics and the symmetry of your physics, because of course that's exactly what he hadn't done. He'd assumed that his positively charged particle had to be the proton, rather than following the math of his equation and coming up to the conclusion. And this was then the beginning of the idea of using symmetries as the guiding force, beauty and symmetries as the guiding force in understanding physics, a method that has worked very well in particle physics up to the current day. Okay. In fact, Dirac's model is also fundamental to our understanding of insulators and semiconductors. And of course, when an electron annihilates with a hole in a semiconductor to produce light, it's exactly the same process as the annihilation of an electron with a positron in the physical vacuum. Okay. So this is where the community was in 1932, just 8 years after the marvelous year in quantum mechanics. It's rather interesting that up until the 1920s at Cambridge, J.J. Thomson would hold an annual party, dinner party, to celebrate the discovery of the electron in 1897. And they would have an annual toast, and the toast was, to the electron, may it never be useful. Of course, it's turned out a little bit differently to that. The early triumphs of quantum mechanics, of course, are amazing lists from the periodic table and all of chemistry, the hardness of matter, the exclusion principle, band theory, field theory, antimatter, semiconductors, and superconductivity, although it came slightly later. And technology, well, it's staggering. The semiconductor industry, which, as you know, is keeping the economy of Phoenix, Arizona alive these days. Moore's law, lasers, LEDs, neodymium magnets, which make electric motors of great power possible, wind turbines, and today compact tokamaks powered by high temperature superconductors to make the intense fields. And by one calculation, 30% of the US economy depends on quantum physics. And of course, you could argue that it's 100% if you were a reductionist. But the point is that it's had a huge impact. And it's hard to imagine that the revolution could still be going on today. But that's the question I want to leave you with in ending today's discussion. 100 years on, could our understanding of the quantum world be incomplete? And what is there for us yet to discover? Okay. How can we even answer this question? It really is a reflection of our level of optimism. Okay. But there is one way to look back at it, and that's to look back at the historical record, the insight from Newtonian physics. In the 17th century, that's the 1600s, the world universe was first introduced into scientific discussion to embody the idea that terrestrial and celestial physics are governed by the same principles. Okay. And of course, this was very, very important. Newton's apple led to insights into the motion of the heavens. His Principia from 1687, first published in Latin, it wasn't translated into a modern European language until about 30 years later, the first language being French. Okay. And 100 years later, in 1787, Newtonian physics was the great revolution that had taken place 100 years ago. And it had led to this exquisite clockwork universe. Lagrangian dynamics had been invented in 1760. And yet, let's look at its incompleteness. Action at a distance ruled supreme. Heat was thought to be a fluid. T equals half mv squared was called v vivra. And energy was a completely unknown concept. Energy was an unknown concept to Lagrange. Energy was an unknown concept to Hamilton. Okay. This, in fact, was the first textbook on the doctrine of energy, published in 1868 in Oxford University Press. The first copies of this paper didn't come to North America till around 1890. Okay. And so, in fact, energy was missing from classical physics until the middle of the 19th century. Okay. And that's a story in its own right, but it makes the point that classical mechanics was incomplete 100 years after its discovery. Okay. So it raises the question, if classical mechanics was woefully incomplete, what about quantum mechanics at 100? So let me spend the last few minutes of this talk telling you a little bit about my perspective as a solid state physicist before ending talking a little bit about the challenge of information and going beyond the Copenhagen picture of quantum mechanics. So in fact, there are many dark matter challenges that face us 100 years after the discovery of quantum physics. Okay. And one of those is dark matter itself, and the fact that 24% of the mass of our universe is dark matter, and 70% is something called dark energy, and we don't understand either of these elements. We're trying to look for them in experiments. The other aspect of this is that just as pre-quantum mechanics, we had a beautiful periodic table put together by Mendeleev based on the observation of the physics of chemistry, we have a beautiful periodic table today that goes beyond the standard model and seems to unify leptons and quarks into quartets, 3 quartets. 2 of the particles, the quarks, are confined, and the other 2 are free, the leptons. Okay? But we don't know what the microscopic origin of this quartet is, but we have this belief that it comes from some deeper, more fundamental theory of the vacuum. We also don't understand quantum gravity. And so these are the celestial challenges we face today. But we also face terrestrial challenges. And maybe they're 2 sides of the same coin. Let me show you one of those terrestrial challenges. This is the strange metal. This is the linear resistivity seen in a cuprate metal, a high temperature superconductor. It's absolutely linear over a wide range in temperature. And this is the fabric of a high temperature superconductor. The scattering rate of the particles that give rise to this beautiful linear resistivity is determined by the thermal energy uncertainty principle, the fact that there's a thermal uncertainty K Boltzmann T, and therefore tau looks like H over K Boltzmann T. We call this Planckian dissipation, and it's a matter of great fascination to understand the origin of this Planckian dissipation. Cutting-edge papers being published in the highest impact journals are coming out every year at the current time. Here's another strange thing that fascinates me. This is samarium hexaboride. This is something that Ona Ayrton and I have worked on, and it has the feature that it's not only a topological insulator with a conducting surface, but it has a very weird feature that it exhibits the quantum oscillations characteristic of a metal, even though it's an insulator. Okay, and so it appears to have some kind of neutral Fermi surface. Where is this coming from? Okay, and there's also a remarkable link between quantum mechanics and phase transitions. There is a kind of phase transition driven by zero-point motion called a quantum phase transition. This particular metal, ytterbium, rhodium-2, silicon-2, is rather remarkable because this is a magnetic phase transition that can be suppressed to zero by field. And you can see in this region here, this orange region is the region of the strange metallic behavior. This region here is a conventional metal, okay? And there's a link between these vortices, this vortex, and the quantum phase transition driven by quantum critical motion. And just as the problem of classical criticality was an unsolved problem in the early 1960s, today the problem of quantum criticality is an unsolved problem in many-body physics. And it has a deep link with high-temperature superconductivity, the cuprates, the iron-based superconductors, the heavy fermion superconductors, and most recently, the twisted bilayer graphene, all exhibit this kind of strange metallic behavior in the vicinity of quantum phase transitions. And it's a link that challenges condensed matter physics, terrestrial physics, to its core. And it suggests the potential for qualitatively new advances in our understanding of quantum matter and the cosmos. And this will require new ideas, new qualitative ideas, the kinds of breakthroughs, the kind of inventive thinking that drove the early quantum mechanicists 100 years ago are needed today. Okay. So let me end by just talking about the other side of this coin. And one is that we live in the age of information. And it's rather interesting that quantum mechanics itself played a major role in the birth of the information age. Here is a picture of John von Neumann with Robert Oppenheimer in front of the, I think it's the ENIAC computer, built at the Institute for Advanced Study in Princeton. And of course, John von Neumann, although he wasn't in my list of early quantum mechanicists, played a major role in establishing the mathematical foundations of quantum mechanics and the digital computer. It's rather interesting that Turing, who was the other man who influenced the early computer, was also interested in quantum mechanics at the time when he died in the 1940s, maybe 1950s. Here is Rolf Landauer, who some people call the godfather of quantum information. He was a leader in the theoretical group at IBM, Yorktown Heights, and he pushed for understanding the physical nature of information and for trying to develop an early version of the quantum computer. And so today in the 21st century, we're fascinated by quantum information. We're also fascinated by the connection between quantum information and natural quantum materials. And we're studying these quantum materials to provide insights into how we may control the quantum physics of entanglement. We're also interested in the nature of information itself. In the 1940s, Shannon developed a theory of channel capacity relating the signal to noise ratio to the channel capacity of a classical information conduit, the fiber optic, for example. In the modern context, we have to think about how information is carried by quantum states. And this has been a very active area of discussion. But one of the key questions is, how is information physical? Okay. Today's theories of quantum information use entanglement as a proxy for information. And they raise the fascinating question, is information an emergent property like entropy, or is it an intrinsic microscopic property of physics? Would it be there without people to make the observation? Would information be flowing? We don't know the answer to these questions. And last and not least, these early quantum mechanicists developed a framework, a philosophical framework for dealing with quantum mechanics, and it became known as the Copenhagen principle. So today we are asking, could there be something beyond the Copenhagen picture of quantum mechanics? And many physicists are discussing this every so often. And one of the key elements of the Copenhagen picture of quantum mechanics is wave function collapse. And in wave function collapse, if you have an electron in a hydrogen atom orbital in its ground state, its state is represented by this wave description in terms of a ket and the wave function. This is the state. And if we observe it, wave function collapse says we collapse it to an eigenstate of position. Okay. And the probability of finding it at that position is psi squared. This is the canonical Copenhagen picture. But there is another view of this, and this is exemplified in a marvelous article by my namesake, no relationship to me, Sidney Coleman, who towards the end of his life thought a lot about the foundations of quantum mechanics. And he didn't believe that wave function collapse or reduction was an important component of quantum mechanics. And this is what he wrote in this marvelous article, Quantum Mechanics in Your Face. It was never published, but you can find it on the archive. And he wrote that now people say the reduction of the wave packet occurs because it looks like the reduction of the wave packet occurs. And that's indeed true. But what I'm asking you to consider in the second part of this lecture is what it would look like if it were the other way around, if all that ever happened was causal evolution according to quantum mechanics. What would that mean in this particular case? Well, it would mean that the wave function would evolve, and the process of observation would then mean an entanglement between the position of the electron and the brain. In fact, if I looked at you as a quantum mechanical robot observing an electron in a hydrogen atom, I would have to assume that you're governed by the principles of quantum mechanics, and therefore you're observing, and it's a causal evolution of the wave function, and therefore your observation must be an entanglement of your brain with the atom. And of course, if I then ask you about what you saw, where you saw it, I am then treating you as an ancillary qubit in the modern language of quantum information. But you see, Coleman's viewpoint runs directly into a contradiction with what we observe. We cannot regard ourselves as illusions, because then that would make a nonsense of our thought, of our thinking about the world. And of course, Descartes made this a central precept of his view of modern philosophy. I think, therefore I am, or in the modern context, I observe, therefore I am. And the signal reality that each of us witnesses is starkly different to Coleman's unitary universe. So where does that leave us? Well, there's room for lots of speculation. One of the most interesting speculations I've heard in recent times is a discussion by Matthew Fisher, who has speculated that nuclear quantum spins may play a role in brain operation. And his argument for this is based on one of the most successful drugs for bipolarity, which is in fact an element, lithium. Lithium is the drug for bipolarity, and Matthew, who is seriously honest, has told us that he suffers from bipolarity, and he took lithium, and it helped him with his problems of depression. And he then wondered, well, how does this work? It's just an element after all. And it turns out there's some evidence that lithium-6 is the active ingredient, and that lithium-7 and the other isotope of lithium plays no role whatsoever in the action of lithium. And this is known because lithium-7 has been given to rats, and they've seen the difference between what happens to rats fed with lithium-7 and rats fed with lithium-6. Of course, these two isotopes have different masses, and therefore diffusion rates would be different, but the diffusion rates differ by only a tiny fraction of a percent. And so the mystery of why there's a difference between the two is fascinating, and the key difference of these two isotopes lies in their nucleus. And so this leads Matthew Fisher to speculate that phosphorus in the mind has a very long decoherence time of its nuclei and may play a major role in the process of thought, and that lithium, which also has a long decoherence time measured in minutes, may be playing an interference role in that process. Well, this is a radical idea. If you want to annoy any of your biology friends, talk to them about the quantum brain and they will tell you that you've gone nutty. It's such a radical idea that they have the same reaction to it as pre-Copernican Jesuits did to the Copernican idea. And so we don't know whether it's going to have any truth to it. It's a radical idea, but presumably at some point in the second half of the quantum revolution that we are now in, our understanding of the brain will collide with measurement and quantum information theory. And at the same time, we'll start to understand quantum gravity and the strange metal. These are things to look forward to in the second half of this revolution. And the only way to make these discoveries is to believe that there will be a second half in the revolution. Thank you very much.